Welcome back. In today's video, we want to express the following, well, at least express the following expression, equation 1 into equation 2. So to do that, they're asking us to apply the necessary trigonometric identities to show that v of t is equal to the following. So basically, we were given that v of t is the sum of two sinusoids, which is what we have here. And we need to apply the expression or apply the necessary trigonometric identities to show that it is equal to the following. Then for b, we want to transform the expression given by equation 1 to the phasor domain, simplify it into a single term, and then transform it back to the time domain to show that the result is identical with the expression given by equation 2. So the first identity I want to use is the expression or the sum. I think what they call it, sum and difference. So that is going to be cosine of omega t plus or minus phi is equal to, and let's include a for a coefficient, a times cosine phi times cosine omega t minus our plus sine phi times sine omega t. So we can go ahead and start expressing our expression by using the necessary trigonometric identity to then find this expression. So basically what we see here is that we're trying to combine both of these if it's going to equal to this one single term. So starting with equation 1. So equation 1 is equal to, after we apply the first trigonometric identity, it is equal to 4 times cosine 30 cosine omega t minus, so we have a plus, so we're going to use the minus, so we can then go ahead, take away the plus, take away the minus, and then follow through. So that's 4 sine of 30 sine omega t plus, so now we're starting with this expression from equation 1. So that's 6 cosine, and that should be 60 times cosine omega t minus 6 sine 60 sine omega t. We can then go ahead and group our necessary terms, and after we do that, we just factor that in 1 and add. So doing that, we can then say that cosine, so our expression that we have here, our cosine, we can simplify that into a coefficient. This can go to a coefficient, coefficient, coefficient. So our first coefficient is 4 times cosine with an angle of 30 is equal to 3.46 times cosine omega t minus, and this is going to be 2. So 4 times sine of 30, that's 2 sine omega t. And we just simplify through the following. All right, we can then go ahead and group and then add. So if we group and add, we end up with 6.46 times cosine omega t minus 7.20 sine omega t. So at this point, I don't believe there are any more trigonometric identity that I can use. So because we're trying to convert that into a single cosine, we know that in our book, whatever book you're using for circuit analysis 2, we can express a signal in the time domain to the phasor domain by using the reference phasor domain counterpart x, which is the first of those properties is that x of t. So let's put x of t over here, and let's put the phasor counterpart x over there. So we know that a cosine omega t can be expressed in the phasor domain as a, just the magnitude of the sine in the time domain, and then a sine omega t can be expressed in the phasor domain as a, the magnitude of the sinusoidal in the time domain, times the complex exponential minus j pi over 2, or j with an angle of minus pi over 2, which then can be simplified to minus j times the magnitude a. So by using that, we can simplify our expression. So we're down here. So we can say that 4.46 times cosine of t, cosine of omega t in the phasor domain is a, which is basically the coefficient. So we include 6.46. Then we have a minus 7.20. And in the phasor domain, we see that we have a minus j times a. So basically what that comes out to is a positive j 7.20. Here we have our expression in the phasor domain. So now it's in the phasor domain, we need to transfer it back to the time domain. In the phasor domain, that's in rectangle form. So we can go to polar form and then to the time domain by using our necessary complex algebra properties. So the first of that is that we can convert that to polar form by taking the magnitude. We take the magnitude by taking the positive square root of x, which is 6.46, plus, and that would be 6.46 squared plus 7.20 squared. So that gives us a magnitude of 9.45 times the complex exponential e to the j phi. And that phi is our angle. So that's the inverse tangent of y divided by x. So we then end up with the angle of 48.1 degrees. Now that's in polar form. We can then go to the time domain by using the identity, which is, that will be a times cosine omega t. So that's in the time domain. And then we can go to the phasor domain by a, the magnitude of the signal in the time domain, times the complex exponential e to the j phi. So now we're in the phasor domain. So all we have to do is just go to the time domain by using that property. So that means a is 9.45, and that's times cosine omega t with a positive angle of 48.1 degrees. So that is v of t. And here you can see that v of t is the expression listed by equation 2. So we have already applied the necessary trigonometric identities to show that expression 1, or equation 1, can be expressed as equation 2. So for b, we can then start with equation 1 again, transform it to the phasor domain, simplify it to a single term, transform it back to the time domain to show that the result is identical with the expression given by equation 2. So this, we're starting with equation 1 again. So notice that we just use the following property. So we don't have to apply, so in this case, we don't have to apply this identity again. We can just start from basically converting our cosine to the phasor domain, because that's the first thing we need to do. Go to the phasor domain. So we're going to apply this property to equation 1. So that means we're going to end up with a, which is 4, a coefficient of 4 times e, j, and that should be 30, plus 6 e to the j with an angle of 60. So now we're in the phasor domain. Now we need to simplify that into a single term. And as always, addition is easiest in rectangle form. So we can simplify that to our rectangle form, or by just using Euler's identity, which we use to get to rectangle form. So Euler's identity is e to the j phi is equal to cosine phi, could be theta as well, plus j sine phi. So we then simplify that to 4 cosine, and that would be an angle of 30 times, and you could factor it out at this point, or you could just go ahead and do it straight. So I'm factoring. So I know that from this expression, if I apply Euler's identity, I'll get a 4. So you can include your a as always. So I'll get a 4 cosine 30. So that's my 4 cosine 30. From this expression, I'll get a 6 cosine 60. So that would be plus cosine 60. Or let's just do it the easier way, the more clear way, so there's no misunderstanding. So we'll just write that out. So that's 4 cosine 30 plus j sine 30 plus 6 cosine 60 plus j sine 60. Not too bad. We could just simplify that quickly. So what we can do right now is that we can add 4 cosine 30 to 6 cosine 60. And as you can see, we'll end up with 6.46 again, this time with a plus. So we can factor out j and add our sine 30 plus 60. So we'll end up with j 7.20. So here we still end up with the same expression. However, though, we didn't take as much step as we did there. So we can then go ahead and convert that to polar form, but we already did that. So basically from here, all we have to do is apply the same technique that we did to get to this expression. So therefore, we end up with the same and that should have been, well, then again, that should have been 45, and that's cosine omega t plus 48.1 degrees. So there we have it. Both steps lead to the same answers, or both route. So we can either use our trigonometric identities and then solve for v of t in the following, or we can just transform to phasor, then go back to time. So we go to phasor. If we need to add, we go to rectangle form, add, and then go back to time. If we want to transform again and we need to divide, so we go to phasor, divide. So we go to phasor, go to polar, and you might end up in polar when you go to phasor. Then you divide from in polar, or you multiply in polar, and then go back to time. But if you need to add or subtract, you go to rectangular, you do that, and then you go back to polar, and then you go back to time. So if you want to add or subtract, you go to rectangle, add and subtract, then go to polar, then go to time. If you want to divide, go to polar, divide or multiply, and then go to time. So that's it for today's problem, and I'll see you in the next one. Bye.